All right, our leadoff speaker after lunch is Steve Senger, talking about those triangular gaps from the talk before lunch.
Oh, fancy. Okay, well, first off, thank you to organizers. Specifically, Mel has been putting up with me for nearly 2 decades. I show up, I talk about something. Mel keeps letting me come back, but so this time it's actually something sort of relevant to combinatorial and additive number theory. So as he mentioned in his talk, there were these sort of bizarre triangular gaps. So I at least fervently believe that I've answered this question to some degree. So at least about the spikes, not about the sort of fractal stuff underneath. I have some ideas about that. But before I get into the talk, I'm going to do some ushy-gushy stuff. So I've been coming here for nearly 20 years, and one of the people I was most excited to see has just passed away. So this is a horrible picture of Bob Donnelly. And I chose this horrible picture because this is the same picture. And I just want you to see this is a group of many people who are here either presently or virtually or in spirit or whatever. And you see Bob's right at the center. So spent a lot of time with Bob over the years. I never did mathematics with him explicitly, but I think this is kind of an image of what this conference means to me. I keep coming back here every single year. I'm spending 2 months in Asia this year, and I flew back here just for this conference. And so my one chance this year to see my kid, I'm like, all right, well, we're going to New York. I mean, he wasn't complaining too much. In New York. I don't remember where. Yeah, somewhere nearby. Yeah. But yeah. But so yeah, this hit me kind of hard. I was really surprised. So I'm quite clearly dedicating this talk to Bob. He's already sorely missed. So feelings, friendship, etc., crying. Let's move on. What I'm planning to talk about today, if you'll let me, is sort of the first 2 pieces, and then like a quick third piece. This what I've been doing with this talk is I've been including an appendix on the slides. I don't plan to go through this, but if somebody has a quick question, there are some answers there. And more appropriately, if somebody finds these slides later and they're wondering what in the heck was going on with lemma 1, then there are sketches of proofs in the slides. I don't know, that bothers me. I'm looking for an answer. I see a great set of slides, and it's just like, oh, this theorem is in some paper somewhere. So here, don't worry about section 4. It's just for other people. Okay, I'm going to sprint through the notation because most of us should know a lot of this notation. And the big thing is going to be giving you the idea of the proof, which has just a few different parts. And there are going to be a couple of, well, basically one picture shown 3 times to show you where the moving parts go and what do they do. So I'm going to use pretty standard notation for the interval of integers between u and v. I've got this notation from Kevin, which was I'm going to let bracket q choose k be the set of all k element subsets of the first q integers, first q natural numbers. This won't happen too often, but sometimes I'll use A to be a vector whose entries are elements of one of these sets. There are some technicalities that I'm just going to brush under the rug. I might have I'm just going to brush those under the rug. I'm going to use pretty standard notation for a sum set. So A plus A is sums of elements from A, and HA is an H-fold sum set. So A plus A dot dot dot, H times in total. This we're not going to do too much with. This is more setting up for people who are reading the appendix, but some of these quantities and pieces of notation will show up. I'm unfortunately front-loading all the notation, then I'll state the problem. But I'm going to let this mathcal x sub hk be k tuples of non-negative integers whose entries sum to h. And I'm going to call this a sum vector for reasons that will become apparent. So if A is some 4-element subset and X is one of these sum vectors, then if I take the dot product of X with this, like I said, brushing some technicalities aside, this sort of vector notation for A, then I can find the elements of the sum set. So, elements of the 3-fold sum set. So this 1, 0, 2, 0, dotting that vector with this as a vector gives me 1 times 5 plus 2 times 7, which I can think of as an element of the threefold sum set. So this is just a notational trick that I learned from Mel. It's going to come in handy for organizing our thoughts later. You don't have to remember all of the which subscript is what. It's just when you see the math cal x, you're thinking this is a vector which will somehow indicate different elements of the iterated sum set. I've also got this, which is the number of different sum vectors, and that this m sub hk is so named because it's the maximum size of an h-fold sum set of a set of k elements. So the maximum possible size of an h-fold iterated sum set of a k-element set. I have a k-element set, take an h-fold sum set. What's the biggest it could be? I've called this m sub hk, which I sometimes abbreviate as just m sub h, because there are a lot of subscripts flopping around. Okay. The support of a vector, depending on whichever vector we're talking about, is just the set of indices associated to non-zero entries. And finally, we have this representation function, which tells me how often an element shows up in an h-fold sum set. So here I'm representing an element of an h-fold sum set by taking this dot product of these things I called sum vectors and sort of a vector version of a subset of the integers from 1 to q. So I think this is the last slide of character introduction. So if a plus a has maximal size, as we've heard, this is called a Seddon set. So if I take the set A, I add it to itself, and I have all as many possible distinct sums as I could, then that gets a special name called a Seddon set. More generally, if instead of taking just 2 sums, I'm taking h-fold sums, then I'm going to call this a B of H set. And the way that I wrote this is by saying if the size of the h-fold sum set is the maximum possible, that's m sub h comma k, where k is the size of the original set, this is called a B of H set. So B of 2 sets are called Seddon sets. If this maximum expansion keeps happening for higher sum sets, in fact, if it holds for an h-fold sum set, we'll call this a B of H set. So with math cal B sub hk, I'm going to define the set of B of H sets chosen from the first q integers. And these are k-element subsets of the first q integers whose h-fold sum set is as big as possible. B sub hk is the set of B of H sets relevant to the parameters k and q. We're almost through. So if math cal B sub hk is the B of H sets, math cal B star of hk is the sets that are B of H sets, but not B of H plus 1 sets. And this is going to be sort of the primary character in the story today. These are the sets, again, k-element subsets of the numbers from 1 to q, sets whose h-fold sums expand as much as possible, but then as soon as you take an h plus 1 fold sum, there is some collision, or there is some non-maximal thing happening. There something like a plus b equals c plus d, where a, b, and c, d are not trivial rearrangements. This is going to, getting bounds on the sizes of these sets and the behaviors of these sets is going to be pretty much the whole proof. So any questions about B of H set or this particular boundary sets or critical sets? Oh. Did I abuse notate? Is this normally denotes something different? No, this is not. Yeah, not basis. This is Steve was coming up with random names for things, and the set of B of H sets I called just math cal B of H. So, all right, why are we here? So last year, Mel talked about some of the stuff that he spoke about today, and he mentioned some computational results about the sizes of iterated sum sets, as he mentioned today. And in particular, for a fixed h and a fixed very, very, very large q, he plotted the histogram of the size of the h-fold sum set of A for randomly selected sets. These are 4-element subsets from the first Q natural numbers. And as he mentioned, there are these sort of weird spikes that showed up. And I'm going to have a diagram in a minute. But there was this histogram. He plots this histogram and he sees, okay, most sets are B of H sets. That's sort of a generic property. Like we would expect sums to not pile up more than we would expect them to pile up when we are iterating our sum set many, many times fewer than we have elements to choose from. This is expected. What was maybe not so expected is that then the gaps between these spikes seem to be consecutive triangular numbers specifically. It wasn't like, oh, it's a B of H set, and then it's just 1 off from being a B of H set, and then maybe 2 off, and then 3 off, as one may expect. So where do these triangular numbers come from? Well, so the size of your iterated sum set is going to be the maximum if it's a B of H set. It'll be the maximum minus 1 if it's 1 less than a B of H set. But rather than m sub h minus 2, m sub h minus 3, then m sub h minus 4, m sub h minus 2 and m sub h minus 3 seem to occur very rarely. So not very often at all. Then m sub h minus 4 shows up again, quite frequently. So the gap between these two is 1, the gap between these two is 3, and the pattern seems to be consecutive triangular numbers. So the goal for today is to show that these triangular gaps must always occur at least up to the first H spikes. That's what I believe to be just what must happen. Beyond that, I make no claims. So I say thanks to, but really any of these people could have been co-authors, right? So lots of emails with Noah Kravitz, phone calls, and long tech exchanges with Mel and Kevin. So I'm very grateful to all these people for sort of contributing ideas and sort of telling me when I'm making silly claims. Okay, so here's a picture. This is a lot to parse in, so I want to just draw your attention to, I've got some H-fold sum set, and I'm telling you that it's a sum set of 4 elements. And then when I compute its H-fold size, it goes into one of these buckets. And of course, there are many more buckets coming down to the left, but I'm just zooming in on the largest sizes. If an H-fold sum set has maximum size, then it's a B of H set. So that's where we've got M sub H here. If it's 1 off from that, we've got M sub H minus 1. 2 off, 3 off, 4 off. And what I'm sort of cartoonishly exaggerating here is that sort of this is the most common. We expect sets to be B of H sets. Then this is also quite common. But then it sort of dies off for a while, and then boom, we've got something common again. You don't need to worry about the colors just yet, but there's something that Kevin pointed out, which is that this spike is slightly lower than that spike, and I think I can even explain why that happens too. Okay, so the goal for today is going to be to tell you some sort of the main ideas in the proof, then to go back to that picture and sort of draw. So you've seen the anatomy. Now I want to show you the connections between the pieces. And then I'll sort of leave you be with some future works. And then if you have questions about how these are proved, this is on the archive. It's been submitted. But there are also more answers in the slides. So if anyone is like, I just don't see how you prove lemma 1 part 2, okay, there are sketches in the slides, so you don't have to read through the whole tech preprint. Okay, so the first sort of big idea is a boundary set count. So if math cal B sub H is the B of H sets that consist of K elements chosen from the first Q natural numbers, these are the B of H sets, and these are the boundary sets. These are the sets that are B of H, but not B of H plus 1. So B of H star, or B star HK, and again, I'm suppressing the parameter Q. Q is very, very large. So how many sets are in each of these boundary classes? So given a Q sufficiently large with respect to H, which is at least 2, we have sort of 3 statements. So statement 1 is that, okay, first, how many quadruples are there drawn from Q elements? Q to the 4th. Now, how many are B of H sets, but not B of H plus 1 sets? No more than Q cubed. Also, at least Q cubed. Again, this is big O. This is standard big O. I'm hiding multiplicative constants. And actually, in an earlier draft, I've kept track of how those constants depend on h, but I've suppressed that for it's just too many pieces flying around. So these two together tell me for each h, there are about q cubed sets in that boundary class. So these are sets for whom the h-fold sum set is maximal size and the h plus 1-fold sum set is not maximal. Third piece is that if I've got one of these boundary sets and I look at the h plus 1-fold sum set, losing more than one from the maximum is very rare. Okay, typical sets. First off, the most typical set is B of H set. That's of size q to the fourth. Next most typical for these boundary sets is there are q cubed of them. Now, what does it mean to be a boundary set and then fail hard at the next stage? Well, that's quite rare. Only q squared times does that happen. So putting this together, what do we expect? We expect that if I fix an h, I can find these boundary sets, that is, these sets that are B of H, but not B of H plus 1, and then they should just fail by one element to be a B of H plus 1 set. That's what sort of should happen. Okay, so that's a technical lemma. I'll just tell you that follows from, most of that follows from viewing these sets as elements of z sub q to the fourth. So this is the 4-dimensional lattice, and I'm chopping off at size q. Entries can have size no bigger than q. And then what does it mean for two elements of the sum set to have the same valuation? Well, that's taking dot products with two different vectors. So I'm looking at hyperplanes in 4 space and how do hyperplanes in 4 space intersect? Well, they intersect in lower dimensional hyperplanes unless they don't. And so this is a lot of just sort of basic geometry on lattice points. Okay, the next thing, which I think this is really sort of the why. So the why do triangular gaps occur? And I'll be going through sketching a proof of this, because this is like during Mel's talk last year, I almost raised my hand and said, "Oh yeah, I know what's going on." So this is essentially what I believe is the why. So the boundary set behavior. So we've already got a boundary set count. Now we want to say what happens after the h-fold sum. So this is a B sub H star set. It's a B of H set, but then something happens at the next stage. What am I quantifying here? At H plus 1, I'm going to be no bigger than the maximum minus 1, that's just the definition. Then when I do an H plus 2-fold sum set, I'm guaranteed to lose more than just 2 elements. I'm actually guaranteed to lose more elements. And if you think about it for 2 seconds, you can see why, but I'm already going to move on to the next slide, and then I'll tell you why in a little bit. Finally, and this was the last piece, so Mel invited me to talk in October, and I said, yeah, I can rigorously prove the first gap, which is not very interesting. I can rigorously prove that the 2 largest big classes are 1 apart. Like, not very surprising. But then in preparing for that talk, I realized that some construction that I had previously could be sort of modified in a very slight way to get the rest of those first H gaps. So this is the so-called construction lemma. I'll put it on the screen just so you see how simple it is, the proof, but I'm not going to go through it carefully. Basically, it says how many of these boundary sets actually sharpen lemma 2. So what do I mean? I've got some count on these boundary sets. There we are. I've got some count on these boundary sets, and I've got some count on the boundary sets that are somewhat pathological, but now I'm going to get a more careful count of these so-called pathological sets. Okay, so what happens in an H-fold sum, what happens to a B of H star set after the first sum beyond that, the second sum beyond that, and then what are the things that happen that exactly agree with that? So lemma 2 says this is the extreme behavior possible. I keep hitting the wrong button, that's on me. This is the extreme behavior possible, and lemma 3 is going to say also that happens a lot. In fact, that happens q cubed times.
People who are watching on Zoom can't see the...
Excellent news. That's good. Okay, thanks for the heads up. So this is an equal sign. On the previous screen, we had a less than or equal sign. So this construction took this was probably the thing that took me the longest. It's not that hard once you know how to do it, but just this was as Kevin and Mel might recall, I was in Vietnam and I had this sort of crisis of belief, and Kevin was like, well, there's this thing that could happen. And this is sort of what deals with the conspiratorial bad sets. Is they might be there, but we still have many sets that are not conspiratorial evil. This does imply lemma 1 part 2, but it also implies more. Okay, so here are the main theorems, which I realized I'm just about out of time. So I think I'll state the main theorems, I'll tell you the gap lemma, and then we'll get to the end. The main theorems are theorem 1, what you expect happens for the second largest frequent set. Theorem 2, this continues to happen. And if you couple that with the count on B of H sets, you get exactly these triangular gaps. So here's the picture you saw before. Now here's the anatomy. So lemma 2 gives us this gap. Lemmas 1 parts 1 and 2 give us this. Lemma 1 part 3 tells us these are low. Lemma 1 parts 2 and 3 give us this. Again, these are upper and lower bounds, upper and lower bounds. This is from the B star H minus 1. This is from B star of H minus 2. Oh, right. People in Zoom land can't see that. The blue is the behavior from the boundary sets at H minus 1. The pink is from the boundary sets at H minus 2. If you put all this together, you get that the first H gaps in these spikes have to be triangular numbers. So rather than going through this, I will push to the proof of the gap lemma. The gap lemma basically comes from as soon as I have, so this is just a quick example. This is a B of 2 set, but not a B of 3 set. So I have 1 plus 1 plus 10 equals 2 plus 2 plus 8. The gap lemma says as soon as I have something like this, now when I go to the fourfold sum set, I can add 1 to both sides, and those are different collisions. I could add 2 to both sides. Those are different collisions. I could add 8 to both sides. I could add 10 to both sides. And in fact, there are 4 things I could add to both sides that must happen. And I could have additional collisions. Now, if you extrapolate this out to further iterated sum sets, you're going to get, well, now if I look at the 5-fold sum set, I could add 1 and 1 to both sides. I could add 1 and 2 to both sides. And that simple counting gives us the discrepancy in the upper bound on the gap lemma. So that is this I plus 2 choose 3. That's where the triangular gaps come from, because as soon as I'm not a B of H set, I'm probably losing 1. That's the most likely. We show that rigorously. And then if I'm losing 1, I must lose 4 at the next stage. And I must lose 10 at the next stage. So I must lose successive tetrahedral numbers whose consecutive differences are triangular numbers. And that is explaining more carefully. How do we prove this rigorously? And finally, really interesting words. So that explains everything for the first 2 carefully. Then how do we get the subsequent gaps? So I want to conclude with future work. Okay, it stands to reason that similar gaps should appear in iterated sum sets for larger sets A. So I'm currently working on the case size of A is 5 with these people, including Steve Miller, a frequent CANT collaborator. So I would ask that if somebody's like, oh, I can already see how to do the 5-fold case, please think of the children. So we're actively working on this. I would like to for them to have a nice project to either write a paper or give us a concrete reason why it won't work. So we expect tetrahedral gaps as opposed to triangular gaps by just following the same reasoning through, but adding now 5 things to each side rather than 4. So with that, thank you so much for your time. Yeah, 1 minute over time.
Are there questions for Steve?
Yeah, Kush.
You said that quite a few of you working on some sort of time, so that's genuinely
I don't believe so. So my current belief, so I've intentionally not thought about it so that undergraduates could do it. So the sort of technical piece of this is not hard. It's intersecting hyperplanes in 4 dimensions. Okay, I mean, maybe you don't do it off the top of your head, but you can get pretty quickly, you can get to some rigorous proofs of those upper and lower bounds. What we think is that the same crap will happen in 5 dimensions and then maybe 6 dimensions, but there could be some symmetry that breaks down and maybe some other peculiar thing shows up. And I've intentionally not thought about it, so hopefully the undergrads can find whether there's a monster or not.
Another question from the room or from Zoom? All right, let's thank Steve again. And our next talk is in 3 minutes. Elisa Sidunova.
I have a USB stick.
All right.
Yeah, after yesterday we were like, okay, it's better this way.
I know just what to do. Talk slides?
Yes.
And that's the right file.
Yes.
Chat. No, I didn't. Sorry. About getting the files off. Yeah. I know in the past I've just logged into like my Zoom account, and then there's like some catalog of preferences that has like 1,000 different things you can do, and one of those is a link to your where it's storing your cloud stuff. Sharing? Yep. But I just got to hit the record button and then we can go.
Your Zoom looks different from my Zoom.
It's his Zoom.
Okay, your Zoom looks different from mine.